Hello and welcome to day 13 of my Advent of Code series for the year 2020. So if you've missed any of the previous episodes, check out the playlist linked right up there to get caught up, and be sure to get subscribed to my channel and turn on post notifications so you don't miss any future videos. So today we are going to tackle day 13, Shuttle Search. I kind of accidentally stayed up for this one. I started about 20 minutes after the problem came out and still came out in the top 1000, so that's an indication of how difficult this second part is to wrap your head around. So here the idea is our ferry has landed safely at that safe point we found yesterday, but now we still need to get to our island, and the only way to do that is by going through the airport here, and to get to that airport we need to take this shuttle service. So our input here is going to be a number which represents the earliest timestamp that we can depart, and then several bus IDs here, where the bus IDs also correspond to how many minutes it takes that bus to go on a round trip between a stop and the airport. So what we are going to try to do here is find the bus ID and the earliest time that we can actually depart. So that's going to be a time after this timestamp right here that lines up with whatever bus ID ends up being the optimal solution. And we need to multiply those together for our solution. So there is an example here on this page right here if you haven't read that yet. And I highly recommend you give this part a try on your own. This part is definitely doable for anyone, and I think you guys should be able to go ahead and finish it up. But then we're going to jump into my code right about now. So the first thing that we have here is how I'm actually reading in the data. So I'm doing that is I'm reading in the lines, and then I'm returning a pair here, where the first thing is an integer representation of that number on the first line, which is our earliest time to depart. And the second part is just a list of the objects of the on the second line split on commas. So next we jump down into our part 1 code. So in the main function, I named these two earliest and IDs as a list. And what I'm doing here is in part 1 first, I am filtering down that list, getting rid of all those X's because they're not applicable to this problem, because those are buses that aren't in service. So I filter all of those out, and then I turn every element in that list into an integer, and then I turn it back into a list. So then what we are doing is essentially I am trying to find which bus departs closest to that earliest departure time and how far away from that earliest departure time it goes. So the first thing I do is I establish closest here, which is a pair where the first part of it is the bus ID itself, and the second part is using this calcdist function I wrote to find the distance from that earliest time that it departs. So I initialize that with the values for the first element in the list. And now let's just jump up to this calcdist function and explain what's going on here. So what's happening here is first, if the bus departs on that earliest time, essentially. So that means if earliest modulus, whatever the bus ID is 0, then I just return 0. And I need that for this second little algorithm right here that I wrote to work. So what we're doing here, I'll break this down into parts. First, we have this earliest floor divided by I. So what earliest floor divided by I is it is essentially the last timestamp before the earliest timestamp that we're given that our bus ID hits. So for example, if it departs every 13 minutes and our timestamp was, I don't know, 27, right? Then this would hold 26 because that is the first time that it departs. So since that 26 timestamp is what is happening, this will hold 2 because that is the second cycle of the bus ID 13. So then what I'm doing is I'm adding 1 to that. So that's representing the first time after this whole thing together is then representing the first indice of that bus's travels after the earliest time that it is going. So then I am multiplying that by the bus ID itself. So that is going to give us the actual timestamp that it is on that run through. And then we are subtracting that earliest time to find the time difference between the earliest time and the bus ID and what time that bus ID actually goes. So then once we have that, what I'm doing here is I'm just looping through the rest of the bus IDs in our list. And I'm saying if that distance is less than whatever's held in this closest thing, then we go ahead and replace it with the bus ID and its distance. And then at the end, we can just simply return that bus ID multiplied by its distance because that's what the problem asked for. So now we can jump over to part 2, which is much more difficult. So the Shuttle company is running a contest, 1 gold coin for anyone that can find the earliest timestamp such that the first bus ID departs at that time, and each subsequent listed bus ID departs at that subsequent minute. So to break that down using this example here, that means that the first that 4-hour timestamp, it has to be divisible by 7 essentially. The 7 bus has to depart at that exact timestamp. The 13 bus has to depart exactly 1 minute after that timestamp. It doesn't matter what departs 2 minutes after. The X's mean that there are no constraints on that, nor for 3 minutes after. But then 4 minutes after, the 59 bus has to depart. 5 minutes after, it doesn't matter. 6 minutes after, the 31 bus has to depart, and 7 minutes after, the 19 bus has to depart. So you may not know where to start with this. It kind of has a worked example here, but obviously it's not going to give away how to actually calculate it. But if you want a sort of hint as to what you're looking for, there's a concept in number theory called Chinese remainder theorem that is essentially this entire problem right here. So if you aren't familiar with that yet, if you familiarize yourself with that, then this problem will become extremely clear in terms of how to do. Clearly, a lot of people already, even the people who stayed up for this, are not as quick on that. So you can definitely do it. So this just gives some examples. Go ahead and give this a try on your own, and we will jump into my code and hopefully an explanation of Chinese number theorem, if I can do it well, right about now. So for part 2, I have this Chinese remainder function right here, and this is a modular multiplicative inverse function, which uses a version of the extended Euclidean algorithm. Again, look these up, and I will leave Wikipedia links in the description if you want to read up on these algorithms. I do not have the time nor the expertise to explain them well. So now if we look at the actual part 2, what I needed to do here is I needed to build the 2 lists that are needed for the Chinese remainder theorem. So what I'm doing here is I am looping through my IDs list, which we got from there, and I need the index and I need the value. If the value is not in x, then what we do is we append to n the int version of x, and we append to a the difference between the indices. So the indice, if you remember, is essentially the modular difference that we need to have between our timestamp and that time. So we are adding to our list the actual time itself minus the time between the timestamp and this time that we need. So then what we're doing is we're just returning the Chinese remainder theorem application of these 2. So now if we jump up to the Chinese remainder theorem itself, we will deconstruct how it works a bit. So what we do is we initialize a sum at 0, and then we have product, which is using math.prod to find the product of all of the elements in that end list. So then what I'm doing is I am using the zip function here to loop through both the n and a lists that got passed in simultaneously, and assigning those to be I and j. So then what I am doing is we have p, which is going to be the product of the entire list, divided by whatever we're up to in that n list. And then we have our sum, which is going to get added to it, j, which is whatever we're up to in that a list, times the modular multiplicative inverse of p, which is that product that we found just then, and I, and then we multiply p back in so that we are essentially just getting, the multiplicative inverse of these 2 times p is going to be, it's the modular reciprocal of I think. So we are adding that product into our sum, so j times, I think, the modular multiplicative reciprocal of I and p. So then finally at the end of that, what we are doing is we are returning the sum modulo the product, because what we're saying here is that sum is going to hold a number which represents sort of all of those times together, and that product is going to be a naive solution. And what we can then just go ahead and say is once we modulus those together, we get the lowest number for which the modulos of all the things in the n lists are able to be added to the things in the a list to yield the things in the n list. Again, I don't think I'm the most qualified person to explain this. There are probably explainer videos. If I find a good explanation, I will link it. And if not, then read the things on Wikipedia, and good luck. So then in terms of the modular multiplicative inverse, this is an application of something called the extended Euclidean algorithm. Again, I'm not the most qualified to explain this, but essentially we need the initial state of the first number, and then we initialize two things that are going to alternate. If that b is equal to 1, we can actually just return 1 as sort of a base case, except for this isn't a function that requires a base case. So then while a is greater than 1, we are going to assign a quotient to be a floor divided by b, and then a and b, we're moving what was in b into a, and a modulo b is going to be moved into b. So then we have our things that used to be 0 and 1 are x minus this quotient that we found up here times x sub 0 is going to be moved into x sub 0, and that x sub 0 is going to be moved into x sub 1. So then if x sub 1 is less than 0 at this point, which means that if x sub 0 was less than 1 on the last iteration, then we go ahead and add to x plus 1, we add b sub 0, because that's just sort of a base case to catch, because obviously in a modular structure like this, we're not going to have a negative value. And then finally, we return x plus 1. So that is my sort of bumbling poor explanation, I think, of those two algorithms, but that's how you solve part 2, and that is how you solve this entire problem. I hope you enjoyed this video. Be sure to stay tuned. Things definitely seem to be ramping up after the sort of lull that was yesterday's puzzle, and I'm excited to see where those go, and I will see you in the next one. Be sure to get subscribed to me so you don't miss any future videos. Goodbye.